Hello everyone, I am Dr. Manju Gupta, Department of Chemistry, St. Aloysius College, Jabalpur. Today I am going to explain Woodwards Fieser Rules for dienes and alpha-beta unsaturated carbonyl compounds in ultraviolet visible spectroscopy. In 1945, Robert Burns Woodward developed some absorption rules for the compounds on the basis of their structure and relate the structure with the value of maximum absorbance for a particular wavelength. But these rules are applicable only for the conjugated dienes and polyenes with up to 4 double bonds. After that, in 1959, Louis Frederick Fieser has modified these rules on the basis of experimental data, and the modified rules are known as Woodwards Fieser Rules. These rules are applicable for the calculation of the value of wavelength for the maximum absorbance may be different from up to 10 to 12 double bonds. According to these rules, the calculated lambda max value may be differ from observed value by 5 to 6. These rules are used to calculate the position and maximum wavelength for a given structure by relating the position and degree of substitution of chromophore. That means if a particular molecule has a carbon-carbon double bond or 2 double bonds are in conjugation, that means it is a diene. And if any of the substituent or structural modification is present in the molecule, then what will be the effect of these structural modifications and substitutions on the value of lambda max of a particular compound. These rules are given for 3 classes of compounds. First, conjugated dienes and polyenes. Second, alpha-beta unsaturated carbonyl compounds. And third, for aromatic compounds and benzoyl derivatives. For each type of diene system is having a certain fixed value of wavelength at which absorption takes place. This fixed value of wavelength is known as base value or parent value. This is the fixed value for a particular molecule. The contribution made by various substituents or structural modifications, and these contributions are added to the basic value to obtain maximum wavelength for a particular compound. According to Woodwards Fieser rules, the lambda max of a molecule can be calculated by the following formula. First, the fixed value of the absorption, that is base value, plus summation of all the substituents attached with the parent molecule, plus other than substituent, summation of any other structural modification. Only the substituents attached to the parent molecule will affect the value of lambda max. If any of the substituent or structural modification is not directly attached with the parent molecule, then it will not affect the value of lambda max. Before going to discuss the rules, first we discuss some terms related with Woodwards Fieser rules. First, homoannular and heteroannular dienes. Homoannular dienes are those in which, in case of cyclic compounds, if conjugated double bond is present in the same ring. This is the example of homoannular diene in which in the 6-membered ring, 2 double bonds are present. So this is a homoannular diene. Or in case of open chain molecules, cis diene is known as homoannular diene. Whereas heteroannular dienes, when the conjugated double bonds are not present in the same ring, 2 double bonds in the dienes are in conjugation, but they are not present in the same ring. This is known as heteroannular diene, or in case of open chain compounds, trans dienes. When the double bonds are not in the same phases, this is known as heteroannular diene. Exocyclic double bond. Exocyclic double bond, generally if the double bond is present in the ring or attached with the ring carbon, then on the position of the double bond, we can consider the double bonds as two types, endocyclic and exocyclic. Endocyclic, when the double bond is present within the ring, then obviously it will be the part of the ring. Exocyclic double bond, the double bond which is present outside of the ring, but any of the double bonded carbon is a part of the ring system. Endocyclic, which is present within the ring. Exocyclic, which is not present in the ring, but any of the double bonded carbon is a part of the ring. For example, this is the example of conjugated diene. Two rings are present, A and B. In ring A, a double bond is present in the within the ring, so this is the endocyclic double bond. Same in the B, this bond is endocyclic. But for the ring A, the carbon involved in the ring is having a double bond that is present in the ring B. That means two carbons are common for ring A and ring B. The bond which is present in the ring B, it will be exocyclic for ring A. So that means ring A has one endocyclic. This is endocyclic double bond, and this is exocyclic double bond, because this double bond is not the part of the ring, but this carbon is a part of the ring. That is known as exocyclic double bond. And ring B has only one endocyclic double bond. Extension of double bond. Since we are discussing the rules for dienes, when in diene molecule any extra double bond is present in the conjugation. Conjugation means alternate double bonds. So when in the diene molecules any extra double bond is present in the conjugation, this is considered as extension of double bond or extension of conjugation. As you can see here, up to this carbon, this is the parent molecule, diene, and after that this double bond is in the conjugation with these two double bonds or the present diene system. So one of the double bond will be considered as extension of conjugation. These are the parent values and increment for different substituents or groups. These are the rules. First is the parent value. Parent value, for the parent value, the parent compound is considered as 1,3-butadiene. It may be cis or trans. For 1,3-butadiene, the value of lambda max is 217 nanometer. Now, the contribution made by various substituents or structural changes will be added to this parent value or basic value. This table shows the increment for a particular structural condition or oxochromic groups. If the homoannular condition is present in the molecule, then there will be increment of 36 nanometer. If any of the exocyclic double bond is present, then the increment will be of 5 nanometer. Extension of conjugation, 30 nanometer. Any alkyl group or ring residue is present with the parent molecule, then the increment will be 5 nanometer. Oxochromic groups. Oxochromic groups, that means they are not chromophore, but they can increase the value of lambda max. For OR group, increment is 6 nanometer. For SR group, 30 nanometer. For chloro or bromo atom, 5 nanometer. And for secondary amine, 60 nanometer. To calculate the value of lambda max, we remember three steps, or we follow the three steps. First, in the given molecule, first we have to select where is the parent molecule. Parent molecule, that means 1,3-butadiene. As in this structure, this is the parent molecule. 1, 2, 3, 4. At 1 and 3 position, 2 double bonds are present. So this is the parent molecule 1,3-butadiene. Second step, mark the groups or structural modification directly attached to the parent molecule. With 1,3-butadiene molecule, which group or which structural modification is present, and for this particular structural modification or group, what is the value of increment? This increment will be added to the parent value. For example, this is a parent molecule 1,3-butadiene. For this, the parent value is 217 nanometer. To the second carbon, one alkyl group is present, and to the fourth carbon, 2 alkyl groups are present. So total 3 alkyl groups are present here, 1, 2, and 3. For one alkyl group, the increment is 5 nanometer. Here 3 alkyl groups are present. So total increment due to 3 alkyl groups will be 15. The calculated value of lambda max will be 232 nanometer. In the same way, in the above second molecule, this is the first we mark the parent molecule. 1, 2, 3, 4. Where is the dienene molecule? So this is marked as parent molecule. Parent value is 217 nanometer. Now, what do you mean by ring residues? So, sometimes ring residues and alkyl groups are considered as same. In some books, ring residue terms are used, and in some books, alkyl group is only used. Ring residue, that means carbon directly, single bonded carbon directly attached to the double bonded carbon. This is the one double bond. For this double bond, this is the single bonded carbon atom is present. Same here, with the double bonded carbon atom, this is the single bonded carbon atom is present. So 2 ring residues are present in the molecule. Other than this, 2 double bonds are present in the same ring. That means diene is homoannular diene. Parent value 217 nanometer. 2 ring residues are present, then the increment will be 10 nanometer. Diene is homoannular. For homoannular diene, increment is 36 nanometer. So the total will be 263 nanometer. Next example. In the next example, again the parent molecule 1, 2, 3, 4. This is the parent molecule. We have to look the substituents directly attached with the parent molecule. With this double bond, double bonded carbon atom, this single bonded carbon is present, 1 ring residue. With this double bond, this single bonded carbon is present, 2nd ring residue. With this double bond, this is the single bonded carbon atom, this is the 3rd ring residue. So for 3 ring residues, 15 nanometer increment will be added, and for the same, for ring A, this bond will be exocyclic. So there is 1 exocyclic double bond. With the parent value, 2 increments will be added. First for the 3 ring residues, and second for the 1 exocyclic double bond. Total value will be 237 nanometer. Next example. In the next example, again you can see the homoannular diene. This is the parent molecule. For the calculation of lambda max, first you have to mark the parent molecule, then you have to search about the increments or groups. With this double bond, this is the 1 alkyl group is present. With this double bonded carbon, this single bonded carbon atom is present, 1 ring residue. With this double bond, this single bonded carbon atom is present, and with this double bond, this single bonded carbon atom is present. 3 ring residues. For 3 ring residues, increment will be 15 nanometer. 1 alkyl group. For 1 alkyl group, increment will be 5 nanometer, and diene is homoannular 36 nanometer. Since your molecule is only up to this carbon, it is not related in any way with the ring, with this ring. So this bond will be not considered as the exocyclic bond for this ring. So the value of lambda max will be 273 nanometer. Next, here 3 double bonds are in conjugation. Obviously, one will be present as extension of conjugation. Suppose if we mark these 2 double bonds as the parent molecule. 1, 2, 3, 4, this is the diene molecule. For parent molecule, parent value is 217 nanometer. First we count the ring residues. With this double bond, this is the first ring residue. With this double bonded carbon atom, this is the second ring residue. If any of the double bond is present in the conjugation, then our molecule will be extended to the extended conjugation. That means parent compound is up to the 4th carbon, but we will consider our parent molecule up to this carbon, and up to this carbon, what are the substituents are attached will be added to the parent value. So this is the first ring residue. This is second ring residue. With this double bond, this single bonded carbon atom is present. With this double bond, these 2 single bonded carbon atoms are present. That means 1, 2, 3, 4, 5. 5 ring residues are present. For 5 ring residues, increment will be 25 nanometer. Now we consider the exocyclic double bond. 3 rings are there, A, B, and C. Ring B. Ring B has 1 exocyclic double bond which is present outside of the ring, but it has 1 double bonded carbon atom. So this bond will be exocyclic for ring B, and this bond will be also exocyclic for ring B. So there are 2 exocyclic bonds for ring B. So increment will be 10 nanometer, and when 1 double bond is in the extension, that is 30 nanometer. So total value of lambda max is 282 nanometer. These were the some examples related to dienes. Second class of Woodwards Fieser rules are also given for the carbonyl compounds. Carbonyl compounds which are alpha beta unsaturated molecules. That means on the alpha and beta position of the carbonyl compound, 1 double bond is present. This is the carbonyl group, and at the alpha and beta position, 1 double bond is present. So this is known as alpha beta unsaturated. Unsaturation or double bond is present on alpha beta position. That's why they are known as alpha beta unsaturated, and molecule is carbonyl compound. So next class of rules are given for alpha beta unsaturated carbonyl molecule, and this is the parent skeleton of the molecule. For this parent skeleton, the value of the basic value or parent value is 215 nanometer. Again, the same structural modifications, and for the functional substituents, what will be the value of increment? First, we look the structural condition. If the diene is homoannular condition is present, then the increment will be 39 nanometer. In case of diene, it was 30 nanometer. Exocyclic double bonds 5 nanometer, extension of conjugation 30 nanometer. Now, the effect of carbonyl group will be up to alpha, beta, and gamma positions. So the effect of different substituents, we have to look at different positions. Carbon adjacent to the carbonyl group, that is alpha position, next carbon beta, third carbon gamma, and next delta and higher position. When the alkyl group is present at alpha position, the increment is 10 nanometer. When it is on beta, 12 nanometer. When at gamma, 18, and for delta and higher is also 18. For OH functional group, when it is on alpha position, 35, at beta 30 nanometer, at gamma 50 nanometer, and higher positions also has 50. For acyl group, 6 nanometer, 6 nanometer, 6 nanometer. O and E group, methoxy group, when it is on the alpha position, 35 nanometer, when it is on beta position, 30 nanometer, when gamma position, 17 nanometer, and when delta position, 31 nanometer. Chloro, when chlorine is present on alpha, then it has 15 nanometer increment, and other than alpha, beta, gamma, or delta anywhere is present, then the increment will be 12 nanometer. For bromo or bromine, when it is on the alpha position, 25 nanometer. When it is on the beta position, 30 nanometer. For gamma and higher, it is 25 nanometer. Now we come to the calculation part. This is the carbonyl group. Carbon directly attached to carbonyl group is alpha, and this is beta. Our parent molecule is substituted up to the beta carbon from this carbonyl group to the beta carbon. So this is the parent molecule from the carbonyl group to the alpha beta carbon. Now we have to look the groups or structural modification attached with this parent molecule. At alpha position, one alkyl group is present. At beta position, two alkyl groups are present. So when the alkyl group present at alpha position, there is an increment of 10 nanometer. When it is present on beta position, the increment is for one alkyl group is 12 nanometer. Since two alkyl groups are present at beta position, so the increment will be 24 nanometer. The calculated value of lambda max will be 249 nanometer. Next example. Carbonyl molecule. Carbonyl, after the carbonyl molecule, this carbon is alpha and this is beta. This is the parent molecule. Now, there is no substituent on the parent molecule, only ring residues are there or alkyl groups are there. From beta carbon, 1, 2, two alkyl groups or ring residues are attached. So this is known as 24 nanometer. In some books, ring residue term is not used. Other than ring residue, only alkyl group is used because they consider with this double bond, this is one of the alkyl group. This whole skeleton is considered as the alkyl group and this whole skeleton is considered as the another alkyl group. So you can use both the terms, alkyl groups as well as ring residues. So at beta position, two alkyl groups or ring residues are present. Increment will be 24 nanometer. The total value of lambda max will be 239 nanometer. Next example. In the next example, our parent molecule is from this carbonyl group, alpha and beta. Our parent molecule is from this carbonyl group to this beta position. Now we have to look the substituents. One alkyl group is present on the alpha, increment will be 10 nanometer. One alkyl group present on beta, sorry, here will be 12 nanometer. And at gamma, there is one ring residue 18, and at delta there is one ring residue 18. This double bond is in conjugation with the parent molecule. So it is the extension of conjugation. Now we consider the exocyclic double bond. Since our molecule is extended up to this carbon, up to delta carbon, since the double bond is in conjugation. Now we can consider this double bond is exocyclic for the ring A. 5. The total value of lambda max will be 249 nanometer. Here you can correct this value. On beta position, there is only one alkyl group. In the next condition, for the next condition, our parent molecule, now you don't confuse with this alpha position and this alpha position. From the carbonyl group, you have to search the conjugated double bond alpha beta unsaturation. For this carbon, there is no unsaturation. So we will look for this double bond. For the parent compound, parent value is 215 nanometer. At alpha position, there is one bromine group is present, bromo atom is present. 25 nanometer will be the increment when bromine is attached with the alpha position. At beta position, one alkyl group is present and one ring residue is present. So the total increment will be 24 nanometer. The calculated value will be 264 nanometer. Few more examples. Search the parent molecule. This is the carbonyl group, alpha, beta. This is your parent molecule. After that, this double bond is in the conjugation. So, parent value is 215 nanometer. At alpha position, there is no alkyl group or any other group is present. At beta position, one ring residue is present. Gamma, delta. One ring residue is present on the delta position. For delta position, increment is 18 nanometer. Two ring residues, one at beta. For beta, increment is 12 nanometer. For delta, increment is 18 nanometer. One double bond is extended. For one double bonded, extended double bond, increment will be 30 nanometer. And this double bond is exocyclic for ring A, 5 nanometer. So the total value of lambda max is approximately 280 nanometer. Last example. This is your parent molecule, carbonyl, alpha, beta. Now you can see after the parent molecule, two more double bonds are in conjugation. So we will take the substituents up to this double bond. Alpha, beta, gamma, delta, delta dash and delta double dash. At alpha position, there is no substitution. At beta position, there is one ring residue. For one ring residue, increment is 12 nanometer. At gamma, there is no substituent. At delta, there is no substituent. At delta dash, there is one ring residue. At delta double dash, there is one alkyl group, 18 nanometer, and one ring residue is present on delta double dash. So two ring residues, one at delta and one at delta double dash. For two ring residues, increment will be 36 nanometer. Extension of conjugation of two double bonds. This is the parent molecule and two more double bonds are present in conjugation. So the two double bonds are in the form of extended conjugation. For this, the increment will be 60 nanometer. When we consider exocyclic double bond, the same for ring B, this bond is exocyclic and this bond is also exocyclic for ring B. So 2 exocyclic bonds for 10 nanometer. So the total value of lambda max will be 351 nanometer. What are the advantages of Woodwards Fieser rules? By using Woodwards Fieser rules, we can calculate the value of lambda max, and this value of lambda max related with the position and degree of substitution of a chromophore. If we know the structure of any molecule by applying Woodwards Fieser rule, we can have an idea about the lambda max, and it will differ only by the value of 4 to 5 by the observed value. This is the main advantage of Woodwards Fieser rules, and it is also used to calculate the position and maximum wavelength for a given structure. Some points must be remembered when we are using the Woodwards Fieser rules. First, if in a diene both the conditions are present, suppose in a molecule homoannular and heteroannular both conditions are present, then the conditions one with the longer wavelength is selected as the parent system. Second, increase in conjugation leads to increase in wavelength, required less amount of energy, and Woodwards Fieser rules are applicable most of the time applicable up to 4 extended double bonds. Thank you.